answer it in a useful way. And then at the end, in case it wasn't obvious through the presentation, I'll go over why should we care, and especially why should you care as transportation engineers.
Your computer is blocking the screen a little bit. Down. There you go.
Yes. Okay, I'm a little bit worried about dropping your computer off the edge of the table. Okay. So for those of you who don't know me, like Laura said, I'm a professor here in civil and mineral engineering. And I'm not a transportation engineer. I'm a geotechnical engineer by training, and then later in my career I got into sustainability. And when they were hiring me for this job, they were like, "Are you a transportation engineer? Because we have enough of those and we don't want any more." And I'm not a transportation engineer. I could not run a 4-step model. It would be not useful for that. But I do a lot of work on transportation infrastructure, because transportation infrastructure is the structure that we put the whole rest of civil society on top of. So that leads to my big research question, which is, given that our infrastructure systems are the skeletal of our society, are we planning, building, operating, maintaining them in a way that aligns with our long-term goals? If, for instance, we have a goal to reduce our greenhouse gas emissions by 80% by 2050, are we building our infrastructure system in a way that gets us there? If we have a goal about equitable access to mobility or accessibility for all of our populace, are we building our infrastructure systems in a way that helps us get there? And overall in my research, I take an inductive bottom-up approach, which means that try and gather a bunch of data and learn from what the data tells me to make over larger theory structured on top of that data about the way in which our infrastructure system works. This means that a lot of my research is dealing with case studies, so very specific what happened in this general case, and then working from there to build bigger theories on top of it. I'm going to give you a brief primer on LCA. I know some of you have taken the LCA class here, and for many people it's very familiar, but for some others it might be less familiar. Life cycle assessment is a tool, it's a thought process for how to think about the overall environmental impact of a product system. And one of the main reasons we take into account the full life cycle is so that we don't have burden shifting. If you think about natural gas, for instance, you've probably heard stories that, well, natural gas is a fairly low greenhouse gas emitting when you burn it. There are lots of processes involved in the getting the natural gas out of the ground that can release a lot of methane, that can have a lot of environmental impacts. So when you take a life cycle assessment, you look at getting it out of the ground, you look at burning it as well, you come up with a slightly different perception of that fuel than if you had just looked at the operation phase. So this is what life cycle assessment is working to get us to do. And it has 4 main stages, which is getting the raw materials, manufacturing it into a product, using the product, and then disposing of the product at the end of its life. And life cycle assessment in North America can be traced back to consumer products. It started with Coca-Cola. Is it better to have plastic Coca-Cola or glass Coca-Cola? And if you look into the impact of the materials, the shipping of the Coca-Cola overall, you have to take into account the weight. You come up with different ideas about what's best depending on which life cycles you include and which ones you don't. This has been expanded over time to bigger and bigger systems. And all the way since the 70s, but a lot in the last 20 years, has been used for built environment products like buildings. And when you're looking at a building, you're looking at slightly different life cycles. So you have extraction and manufacturing, you have delivery to site and the construction on site, which is sort of more manufacturing even once you pass the original manufacturing materials. Then you have operation, repair, and replacement, because buildings have 20, 50, if you live in Europe, 400-year lifespans. And then how do you get rid of the building at the end of its lifespan? And so this is the way in which people have been thinking about built environment LCA for a long time. But when we start to think about transportation life cycles, because of that nature of transportation as the baseline on which we build society, and also because the nature of transportation products is really, really big, right? Even a massive building is not going to have an influence much larger than a couple blocks around it. A transportation system can go all the way through a city, it can go between cities, you can have a highway that goes for hundreds, if not thousands of kilometers, and so the scale of impact we're having is a lot larger. And so we have the impact of the whole construction, so we have to get the materials out of the ground, we have to clear wherever we want to build the transportation infrastructure, and we have to deal with all the transportation disruption while we're building the infrastructure. And then you go up to the things we tend to think about the most often in the little box over here. You have to operate the infrastructure, you've got to make sure the roads stay smooth, you've got to keep the trains running, you've got to run the cars and the trains. And then at the same time, you have all of the important indirect or induced impacts of induced demand on travel behavior, transport land use connections, the way in which our transport system influences or not the protection of natural land. And then eventually you get to a sort of end of life where we start taking our transportation system apart in major ways, but mostly to rebuild it, right? The oldest metro systems in the world are still running. Roman roads, we still use them, right? The major roads in Toronto have been here since the beginning. We don't tend to end of life our transportation infrastructure, so it doesn't fit into the LCA framework in the same way as many other consumer products. And so most of what I'm going to be talking about today is in this space, in part because this space and some of this space is pretty well covered by transportation engineering. But I think it's important that transportation engineers and all of us as we think about planning our infrastructure system have a better ability to think about the whole space as we work towards long-term goals like accessibility for all, not melting the planet, and basic things that we're working towards. So some of you will have seen this before, especially if you were here 4 years ago when I gave my last presentation in the seminar. And so in my past work, I've tried to pick off pieces of this bigger problem and think about what the overall impact is of our infrastructure, in this case, particularly on greenhouse gas emissions. So this is work that came out of my PhD looking at what's the net greenhouse gas emission of the Shepherd subway. And for that, I looked at what it took to build the subway, but also its impact on long-term travel behavior and its impact on land use change. And when we put them all together, I found that overall, you get a big buildup of greenhouse gas emissions during construction, and then you start to recover emissions as people change travel behavior and as land use changes over time. But this was taking the optimistic approach. This was taking a less optimistic approach to induced demand and land use change, and this was taking the least optimistic approach. And if we want to make decisions about how to build infrastructure and what we should be doing with it, this range of it pays back in 12 years to it never pays back is too big. This work, I think, was useful for bringing up questions, but on actual guidelines and numbers, the ranges were all over the place, and you could make a reasonable argument in either direction. So in the time since then, I've been looking at, well, which parts of this data were really weak? And one of the things that you'll see over here is there was no maintenance impact on the infrastructure. I believed in my earlier work that once you build the infrastructure, it keeps going forever without needing any further inputs. What you're seeing there is the impact of electricity, and the reason it goes down is because the change in electricity mix in Ontario over that time. And then another big thing that was missing from our understanding was what exactly was going on in the construction phase. It's a big part of the emissions. It has the major impact on our payback, because if it's bigger, we have more to pay back. If it's smaller, we have less to pay back. But the data that was available in our understanding at the time I was doing my PhD was pretty thin. In part because most of this data is proprietary, and because of the nature of the construction industry, it tends to be held by many different people. And so getting even a basic number like how much concrete did we put in this building or how much concrete did we put in the subway is actually surprisingly difficult. So going forward, we started to ask a couple other questions, and one of them was, do we have enough information about the rail network as a whole, or the way in which we build rail infrastructure, to get an understanding of what the greenhouse gas impact of rail infrastructure is so that we can use this in planning? And when I started to do this work, I really thought the answer was going to be yes. It had been about a decade since some of the key seminal work in this space. A lot of people have been talking about it. I'd contributed to it. I felt we were getting fairly to the end. So one of the things that we need to do to calculate the embodied emissions of building infrastructure, and this is the cradle to place part, it's the part of the life cycle that's just until the infrastructure opens and we start using it, was we need to know how much materials are involved, we need to know how much fuel is involved, and we need to know what the intensity of that fuel or materials are. Like, what's the impact for the environment of using 1 meters cubed of concrete? And so in some early research, when I first started here, we picked off, well, let's look at the maintenance. That was one of the two things that were missing. We know we use a lot of materials in maintenance, or at least we think we probably do, and it hadn't been factored into most of the work that had gone into the life cycle. And so we picked up the Spadina streetcar as a case study, and started looking at the development of the Spadina streetcar over time. And so we now know the Spadina streetcar as it goes from Union Station, it comes out of Queens Quay, comes out from underground, so this part's underground, comes across the waterfront, and then goes up and goes underground again to go into Spadina Streetcar. Somebody poke Matt, he's struggling.
Jet lag.
I believe you. And so we started to look at, well, how had the greenhouse gas emissions built up over time through the various stages of construction, and what had maintenance had to do with it. And so this is what we found overall. And so we're seeing here in black is these are the underground sections. And we didn't find any evidence of underground maintenance, but we found a lot of evidence for the gray sections, which is the above ground. So this was the original construction, and then this was maintenance later. And what we found is that the above ground sections of Spadina have been built twice. And that's kind of surprising. The line hasn't been around for that long. It started construction in the late 80s. But the entire line by the end of our case study will have been built twice, and this is just major maintenance. So what does that do for the environmental payback of that line? Well, if it took 20 years for it to pay back the first time, and then we built it again, and it takes another 20 years, it means we're going to struggle to benefit from the potential savings of the system itself. And so why was this taking so long? Well, there was a couple things. When they first built the Spadina line, they wanted to close the road as little as possible. And so they built it really quickly, which had a durability impact. So when they went to do maintenance, and they thought they were only going to have to maintain the top concrete layer where vibrations from the streetcar had basically meant that the rail lines were not properly encased in the concrete anymore. They thought they were just going to have to do the top. They found they had to do the full depth, which required both a lot more time in the construction or refab process when they had to redo it, but also a lot more materials. And so there's a lesson here about if we're going to do it, let's take the time to do it right, and that's hard. Nobody likes it when roads are shut down. Nobody likes it when transport is out of service. But there had been a challenge the first time around because of doing it quickly that had long-term impacts. One thing I'm going to say right now is I do my research on rail infrastructure because I like rail infrastructure. This applies much, much worse and much more to roads. So nobody should come out of this with a message that rail infrastructure is bad and we shouldn't do it. It's just a framework for thinking about infrastructure. Roads require a huge amount of maintenance as well, and they have all of the cars that go on them. Okay. So going back to rail, we've taken a little bit of a look at maintenance. Now let's look at all of the literature that had been done in the rail space. We started doing a lit review of all of the literature that had looked at the embodied emissions of rail of all types, of light rail, of heavy rail, of metro rail. And we had a couple of research questions going in. One was, where in the world has this research been done? There was a lot of conversation going on, but it was a little bit unclear from the way we were all talking, is this pertinent to everywhere in the world, or is it all just coming from California? What were the main factors influencing the greenhouse gas emissions of our rail infrastructure? Are it things that we can control in planning or control in design? How quickly is our infrastructure paying back its greenhouse gas emissions? And do we know enough from what's already existing that we could make useful models for planning in the future? And the first question was pretty easy. Most of the work has been done in Europe, with the second most coming from North America, and the color coding is by the type of work that had been done. So high-speed rail had gotten the most attention, in part because while this was all happening, a lot of places were talking about, should we build high-speed rail, is it better than flying? And then light rail had also gotten a fair amount of attention, and metro rail. But the other questions were a little bit harder to answer. When we started looking, we found that while there had been 23 papers in this space, most of them had only looked at embodied emissions as part of what they were doing. There were only 4 papers that had made embodied emissions their main focus. And as we all know from when you do papers, if you're doing 6 different things at once, you do each of them with a little bit less detail than if you were only focusing on one thing. So there was a lot less detail out there than we had originally expected. And everybody had done this in different ways. People had taken different boundaries, they had taken different life cycle assessment approaches, they had done it at different stages of construction. And so there was a huge amount of diversity within the data set, and much more than certainly I expected going in. When we took a look at payback periods, again, there was a pretty big range. The one at the top from the 70s should be discounted because it was a completely different energy system at the time. And what we were finding in general is that most people were finding it takes decades to pay back the upfront cost of building rail infrastructure, meaning there is space as we build and plan to reduce the material and greenhouse gas investment so that we can get better long-term payback. And did we have enough information to make a sketch tool? Could we say, if you're choosing light rail versus heavy rail, this is how much greenhouse gas emissions you should plan per kilometer? What we found is that there was a very, very large range in the published work. As you can see, for metro rail, it ranges from 5,000 greenhouse gas emissions per kilometer to 30,000. So you can say, okay, well, this is a huge range, maybe not that useful, but one of the things to notice is that light rail, intercity rail, metro rail are not necessarily descriptors of the type of infrastructure you run on them. They're a label that we give to our infrastructure, and sometimes they tell us a lot about the rail gauge or maybe about the vehicle itself. But are you building a grade, are you building in a tunnel? That wasn't included in these names. So if we backed off and put all of the infrastructure, whether it's called light rail or heavy rail or high-speed rail, into the same pile, and looked at the need for tunneling versus at-grade versus elevated structures, could we reduce some of the variance on all of these data? And what we found was that, in general, tunneling is about 27 times more greenhouse gas intensive than building at grade. And for elevated structures, there's less data, but about 6 times as much. And if we use that to normalize the emissions, you find a much smaller range of emissions for each type of rail. And it led us to, for an equivalent at-grade kilometer, you could make a sketch tool that said it was a little bit under 1,000 tons of CO2 per kilometer, if you look at everything all in. And so we can say, okay, great, we've come up with a sketch tool. You should normalize per at-grade kilometer, multiply by 27 times if it's going to be a tunnel, multiply by 6 times if it's going to be elevated. But to add a little bit of caution to that, when we grouped on various other parts of the infrastructure, for instance, like, was the project already constructed or were they looking at a planned project, there were huge variations in the numbers. So the 941 should definitely be taken with a grain of salt. And so we'll go back to the original research questions, were we able to answer them? So where in the world? Yeah, we know most of it is coming from Europe and from North America. So if we're looking at other places, we should probably put some effort into understanding if those places have meaningful construction differences from Europe and North America. And so what are the published payback periods? It looks like we're looking at a decade to decades. Do we have enough information yet to use this in planning? I would say we have enough information for a very sketchy sketch tool, but not enough for detailed planning. And one of the things the field needs going forward is a lot more standardization, but also a lot more data from the people who build these systems and plan these systems to allow for better studying and more detailed outcomes. And so the next thing I wanted to ask was, okay, it's kind of hard to figure out what's embodied in a construction system. There are challenges with data, there are challenges with boundaries. And there has been challenge with data in this field since the field has existed. It was a challenge for my PhD, it was a challenge for all of the people who came before me, and it's been a challenge in my work my whole career. But there are increasing digitized tools and modern approaches to construction, and maybe we could take a different approach to collecting the data, and it might be easier to get it all together. And so one of the things that's becoming bigger and bigger in construction is the use of building information modeling, which is 3D models that represent all of the components that will go into a building and are usually labeled by material. So if you looked at this drawing, the red, which is the steel, would usually be labeled steel with all of its details. The yellow, which looks to me like the plumbing system, would usually be labeled with all of the material details. And so inside a building information model, you can usually just press a button and it gives you all of the material quantities inside the virtual construction you have just made. And that could be a great way to have a better approach for getting all of the data we need anywhere there is a building information model. So took another case study, in this case a bridge, and we had a BIM model from before it was built, and also a bunch of details from the construction site of actually measuring how much concrete was used on that site, how much steel was used on that site, how much asphalt was used on the site. And we wanted to take a look and see, between these two sets of data, are we going to get the same information? Is the BIM model as good as having the information from on site, and could it replace the complicated, challenging, proprietary needs to collect all of this data by hand? When we took a look at a bridge in Ontario, it was originally 2 lanes of traffic that went over 2 bridges and then had an island and went over 2 other bridges. And the plan was, between the 2 bridges, to build a new bridge, refurbish one of the original bridges, and take down one of the original lanes. So there were 2 new bridges and 2 bridge refurbishments in the project. And overall, it was about 0.5 kilometer long. And this is what the Naviswork figures looked like, which was the building information model we were using. And so looked at the work in 4 different stages. 1, just using the BIM as a base case. 2, adjusting the things that were modeled in the BIM to their on-site quantities. So structural steel is modeled in the BIM, but steel reinforcing is not. Some elements, like construction energy, are not modeled in the BIM at all. So first wanted to just adjust the quantities themselves, then wanted to add in the impacts of things not included, like rebar and BIM, and then in the first case, tested the sensitivity of this approach for calculating greenhouse gas emissions to assumed or preliminary intensities assumed for concrete, right? If we assume concrete has 10 greenhouse gas emissions in it, we know that there's a big range in the way concrete is manufactured, and so we know we needed to test the sensitivity of that 10. And these are the range of results we came up with for the first 3 cases. So BC case is the base case. So if we had just done a greenhouse gas accounting based on the BIM, we would have come up with about 1.25 on that scale. When we adjust the materials for what we observed on site, it goes up. When we adjust for adding in the impact of all of the construction materials on site, it goes up again. And what we were finding in these is the difference between the BIM model itself and what was measured on the construction site was about 208%, which is massive, right? That's not a normal error bar. And so what that means is BIM as it's currently being drawn is not going to be accurate enough for greenhouse gas accounting based on this case study. When we look closer to what went on, why that's a huge difference, right? That kind of material difference is going to be showing up in the economic measures of the company that built this. It's not the kind of thing people casually just let slip by. So when we looked at what the BIM model had said we would need for concrete versus what actually needed, you find out that for a while it traced really well. So the QA/QC quantities were what we had on site, the BIM-based quantities are what we'd expect from the model, and up until about 400 days into the construction project, it was all going along really well. But then what happened is they had to build something extra that wasn't in the model. The project ended up needing a wall, and that increased the concrete percentage by 50%. You see a similar pattern happen also with the steel. Again, they needed to build extra things, so it increased the steel quantity by a lot. And so you would say at one level, well, they had to build something extra. Maybe this isn't a comment on the BIM, it's just this project had to build something extra. But this project is still ongoing, and we've had the same questions. We were talking to the people who built this. We said, how good are you usually at predicting your overall material use? And they said, we're really, really good. This is our bread and butter, we do this really well, unless something changes. And we said, well, how often do things change? And they said, all the time, constantly. And if all the time constantly is true, then it means that these models are not going to capture everything that we want to do with them if we want to use them as a replacement for measuring detailed things on site. And if what we're going to say is this bridge or anything we're going to build has to have an upper bound of this is its allotment, this is its allowed greenhouse gas emissions, then that could be a real problem, right? If you say you're allowed this much, you end up with 300% of that. That's a meaningful difference, especially as we're trying to reduce greenhouse gas emissions aggressively. Also not included in the BIM is the fuel use, right? The BIM usually draws the physical structure. The fuel use in this case was about 30% of the overall greenhouse gas emissions. And so that made a big difference as we finally moved from the BCA case to BCA plus. And you could put fuel use in BIM, and it's something that we're talking about, just saying, okay, well, how should we use BIM for greenhouse gas emissions? You can model where all of the construction equipment will be. It's just not currently standard practice because you don't necessarily need that for construction, so it's a big question of what are you doing the BIM for, and if you're making it specifically for greenhouse gas emissions, what do you have to do differently? So you've seen on here, I drew the error bars of what happens to this when you change the relative greenhouse gas intensity of concrete or steel. And that's a meaningful error, it changes things, but it is much, much less important than getting the quantities right overall. And this is important because in the environmental space for construction, the conversation we're having the loudest is what other materials can we use? Can we use different concrete? Can we use different steel? Can we replace this type of insulation with this type of insulation? And on many levels, that's easy, right? If we can build exactly the same structures and just switch the materials and they have exactly the same performance and it's on the material manufacturer, the concrete plant, to just give us a different mix that does exactly the same thing. For the rest of us, that's really easy. We go about business as usual. And I think that's part of the reason this is getting so much attention. But just like with the 3 R's, right? Anyone who grew up in Ontario, reduce, reuse, recycle. If we can reduce the materials we're using up front, no matter what their greenhouse gas intensity, the overall impact will be lower, and it's not as much part of the conversation. So what we found overall was that there was a major difference, that the fuel itself is really important, and that this has meaningful lessons for how we use BIM for LCA. Absolutely, BIM could do it. We would just have to approach it in a very different way than is currently standard practice. So I've been spending a lot of years doing specific case studies, and that's useful, right? One bridge is useful, but you could easily say, well, that was one case study. Does it apply to other case studies? Maybe only that case study has to build an extra wall and nobody else ever does. And I agree with that question. So where I've come to recently is we can do this for individual buildings. We can do it for individual roads. We can do it for individual subways. Why don't we do it for the whole city, one building at a time? There's 400,000 buildings in the city, so it may take a little while. And so the research questions I'm looking at right now at the city scale are, how much material use are we using in the city? Where are we using it? And is there an optimal urban form? Is there an optimal way we could design the city that would provide a reasonable quality of life, but also reduce our overall material use, or at least our per capita material use, and associated environmental impacts? So this work is ongoing. I'm just going to show you where we started. In case you don't know Toronto, this is Toronto. We started with the roads first because we could get this data mostly publicly available. And so we want to figure out what is the material in all of the roads. Available on the City of Toronto's website is our construction standards. So we can look at, we have this much subbase, we have this much concrete, we have this much aggregate. We also got a map of all of the roads from the city. And then one of my students went through all of the construction notices that had been released over a 2-year period on the City of Toronto website and mapped every piece of maintenance that was being done in the city. And when we took a look at, over time, how much material is in the City of Toronto, both the stocks and flows, how much material is on our roads, and how is it changing over time. And the first time we looked at it, so you can see, in 1997, we put in about 110,000 meters cubed of asphalt into the city, and it goes up and down in huge variation. We thought maybe this is election cycles, where we build a lot of new roads right before the election, but actually we found that until maybe recently, that's not lining up. So it's a little bit unclear why there are such large variations, but we're seeing over time that between 1% and 5% of the city's entire road stock and materials is turning over every year. And so you could ask, is that fast enough? And so if it's 1%, we're looking at, we rebuild our whole road system every 100 years. If it's 5%, it's every 20 years, which is closer to what we've been told is an expected lifespan for a road. So this work is currently ongoing to expand from roads to everything else. I'm currently recruiting postdocs, if you know anybody looking for a job. And the things to add into this afterwards are all of the other transportation infrastructure. Right? Even our road system is made of much more than roads. There's tunnels, there's bridges, then there's all the streetcars, there's all the subways, all of that has to come in. All of the water infrastructure, I'm currently getting piece by piece detailed maps of the entire city's water infrastructure. And then we need all of the buildings, which is, again, more than 400,000 buildings, which we're also working on. That's probably going to require data science, looking at computer vision and also machine learning. So again, tell your friends, it's postdoc. And so why care, right? This is probably not what normally goes on in these lectures. People are usually talking about more traditional transportation engineering, so why should all of you care about all of this construction life cycle assessment stuff? I think you should care because it's interesting, but also the way in which the transportation system is going. If we reach utopia transportation system as currently promised to us, where it's all autonomous, it's all electric, and it's all shared, the importance for the overall impact, both in terms of costs, in terms of social outcomes, but especially in terms of the environment, is going to have it's going to be really heavily related to what infrastructure we're building to maintain these transportation systems. If the cars are clean and everyone's sharing them and they have no impact themselves, then the impact is what infrastructure do we need for that system, and what impact is it having on the way we're building our built world. And I'm sure you have all seen this picture, and I'm sure most of you have seen this picture. But when we think about that, it takes us back to original life cycle framing, right? If the impacts of this part are all gonna go away, but it's gonna demand more land use, more sprawl, more conversion of our forestry to suburbs and roads, and it's gonna require a huge amount of construction and operation, and maybe more input into our infrastructure system so that the autonomous cars can navigate it. And we also have to keep maintaining the infrastructure system over time. Those are big questions that transportation engineers should be thinking about. It's one thing to make an autonomous system work and to make it safe and to make sure that all of the cars can get by. But I challenge you as transportation engineers who will be guiding this transition as we go through it to think also about what are the infrastructure implications of all of these choices? How much materials does that mean in a resource-constrained world? What are the environmental impacts of that? And what is the impact this is also going to have on our land use system? So thank you very much to all of the people who did the detailed work that leads up to this, many of whom are in this room. And that's it from me. I'll take any questions.
Do you, like let's say with a Spadina streetcar, well, because you have the Spadina streetcar in place of a laneway or a couple lanes of roadway, do you include in the benefits part of the equation that you don't have to maintain or those roadways, lanes?
So I never looked at the payback for Spadina. I've only looked at the maintenance cost. Yeah, I think that would be a reasonable thing to include. That is there any more maintenance than you would have had to do on the roads? Because the question of what is the counterfactual is always really important. And of course, as you get farther and farther away from the moment where you made the change, the counterfactual gets more and more theoretical. So no, I have never included that, in part because I've never calculated payback for Spadina. That was just one paper just looking at the maintenance. In part because someone in the city of Toronto was very cooperative for a few weeks until their boss told them to stop. So for a while I was getting a huge amount of information on that line. And then I got a very polite, I am no longer allowed to talk to you email. Yeah, I think it's a reasonable question, but also what else would we have done with that, right? We could have put bike lanes in, we could have ripped it up. But again, I would strongly argue public transportation is the way we have to go. It's leaps and bounds better than private transportation. But we should still make sure we optimize that system to get the most out of it that we can.
So what are the factors that they consider as the payback? So usually
So who's they? Like me?
You or all of those decades of payback, so they just consider reducing vacancy.
It's a big range. Some people just look at people would have driven and now they'll take the subway, and so it's just a switch. In my work, I've always included it has an influence on land use behavior, which means more people are living in denser communities, which has impacts on energy use. That's always been part of my work, unless, for instance, I found no impact on land use behavior, but I've always checked. Some people look at things like changes in congestion overall. The field is really non-standard.
But all of them are considering GHG emissions, not other benefits of
In that table, everybody can looked at GHG emissions. Lots of people also looked at other things like payback for air quality impacts or
social benefits or safety benefits.
No. People in looking in the environmental papers tend to not also include social benefits and environmental benefits and safety benefits. This is supposed to be part of a multi-criteria assessment. I don't think this should be the only way that people make decisions, but we're generally pretty good at talking about economic drivers. I think we're a little bit better in the transportation space about talking about safety drivers, and we tend not to really know how to talk about environmental drivers, at least historically we didn't.
can go from one quick question. So when talking about BIM and changes in construction, changes there, it's kind of inevitable. People change their mind, think like functionality of things changing. I'm not clear, so where do you want to go with this issue? Do you want to, at the end of the day, come up, like, what's your approach in solving this question? There is change in construction, it increases a lot of time the GHG, so what should we do about it?
Okay, well, way to go for the
I
question.
mean, yeah, but I understand
okay,
the
so,
part that
yeah.
BIM is good and all of that.
Yeah, so what should we do for it? I think that we could take a slightly different approach to BIM in the first place. Well, first of all, we should get a whack more data, right? If we want, the built environment accounts for around 40%, sometimes more, of our overall greenhouse gas emissions, and we have very little insight into it because the data on this industry is fractured and held by lots of different people, ranging from the owners and the funders all the way down to the subcontractors and the manufacturers. So if we want to do something about this, which I think we should want to do, we need a different approach to how we communicate information in the field and more access to data, which everyone has been saying for a really long time, and some countries are making steps on, and there are increasing willingness in the field to participate, but we have not yet gotten over that hurdle. So I have one case study. If we had 50 or 100, we would be able to answer these questions more definitively, and then we could know, what kinds of impacts of change are happening. One way to do that would be to shift the emphasis a little bit, be willing to pay for more planning, for more time up front when we're doing things theoretically instead of on the ground. If that was something our owners were willing to pay for, it would be something that people were willing to do, but the field tends to operate on pretty low margins, which push a lot of pressure on soft costs. So that would be one thing. And then another thing would be, if this is a standard relationship, right, if we did the 100 case studies, and it was always, we expect to see a 30% plus or minus 5 increase, then we could just plan accordingly. But because we don't do that, we don't have that information. If it turns out that it's all over the place and there's nothing standardized, then we'll need a new approach. But we don't yet have enough information to answer that. I can point out a lot of questions, I can say what we've done in individual case studies, but we're still working on building the critical mass of knowledge.
And assuming that you finish all of the analysis and so on, how does that, assuming that, and yeah, you're done with your analysis and we have something like carbon tax or something in place, and you would you would push for a law that would say if you make a change in your construction, this is how much you should pay? Where are you going with this?
I don't think I'm not going for a regulatory solution. Where academics are going with this. Well, first off, we're going for knowledge. I would argue that we don't know how to interfere in the system until we understand it, and that we shouldn't be interfering in the system without understanding it. Then in the long term, what does that solution mean, right? The carbon tax will hit the construction industry. It will either hit the manufacturers of products directly, or it will hit the users, depending on how it is eventually structured. But right now, there could be higher costs for fuels, there could be higher costs for construction materials that are greenhouse gas intensive, which could be influencing then people to be more efficient with materials, which could have an impact. I am not saying that we should have a law that says if you build a bridge with 3 tons too much greenhouse gas emission, you go to jail, or we should tear it down. But it's a system that does need engagement with this question, and we can't do it without the information, and where a lot of people are heading, right? So in 2017, the provincial government said that by 2019, life cycle assessment would be a requirement on all major projects. That didn't happen because they are no longer in government, but those types of things are coming, and people don't know how to apply those laws. What's your benchmark? What are we comparing against? How do you know if a construction project is doing a good job or a bad job? We're building up a field of knowledge to help inform those discussions.
So based on this ex-post evaluations, in the end, you can help the ex-ante assessments of the future developments.
Exactly.
So I just wonder how to define the payback period. Then take the summary as a case. It means the emission reduction in the useful is equal to the emission in construction.
Yes. Well, not just in construction. So the question was, how am I calculating what payback is? When do you hit 0? So it means that the emissions that go into making the system exist have been equaled by the emissions that have been avoided because the system exists. And so the system makes emissions through use of materials in construction, use of energy in construction, also use of materials and energy in operation. And it avoids emissions through changes in travel behavior and also changes in land use behavior. And many others, but those are the ones that I've looked at in my work.
When you look at payback, like if you look at cash flow, you usually apply a discount rate.
Yeah.
Do you do that with greenhouse gas emissions?
So
Does it make sense?
it does make sense, and you have certainly discussed it. I use a discount rate of 0 because of the way in which greenhouse gas emissions persist in the atmosphere. You could make an argument about discount factors, especially given that we have many places monetize greenhouse gas emissions. You can make a discount factor tied to the monetization. And you could, and I think that would be a reasonable argument, if your goal, for instance, was to limit your cash hit based on the greenhouse gas emissions of your product. For the goals that I am most particularly interested in, which is averting the most negative impacts of climate change, keeping us hopefully under the 1.5, but ideally, somewhere under 4, then a ton is a ton is a ton.
Yeah, well, except that there is some uncertainty in construction methods.
Yeah.
And you would expect that the methods would improve over time.
Yeah.
And so you'd rather defer greenhouse
Future.
gas emissions to the future when you might have a better technology. Or
Yeah,
something
so
like that.
I avoid that problem by doing ex post work, and so everything I have looked at has been done already. And so there's no chance to improve them, they've already happened. But I think it's a completely reasonable question to think, how should we balance between infrastructure that requires a lot of materials up front now, which is a heavy impact, or things that we could invest in with a lighter touch over time? The thing that I would add to that is that transportation infrastructure has a really big impact on travel behavior and land use change. And the lighter the infrastructure, the less the impact it has, or in some ways the worse impact it has, right? Like roads, automobile system is a really light transportation infrastructure as they go. You can build it whenever you need it, you can extend it really easily, it's very flexible, right? That all sounds like good, light infrastructure, but it's responsible for 40% of the greenhouse gas emissions in Toronto. And where other sectors are doing well, the transportation sector is just getting worse. So I think we have to be a little bit careful about saying light infrastructure is adaptable and will let us solve this problem, because sometimes light infrastructure isn't itself begetting the problem.
If the fuels become more efficient and the machines become more efficient, still the vehicle miles traveled are projected to be increasing more and more.
Yeah, and in Canada, the vehicle miles traveled have counteracted, right? Our cars are better, our engines are better, our fuel is better, but we travel so much more in bigger cars that our emissions are getting worse. And if you take away all of that, there's major impacts on land use change, there's major impacts on infrastructure need. At any time we build a new road, we need new houses, we need new sewer. So even if the car itself was 0 emissions, the impact of driving would still have very significant negative environmental consequences. Okay, thank you for coming.
Thank you.